Look up at the night sky. What do you see? Stars, planets, galaxies, all that beautiful, glowing stuff. But what if I told you that everything you see, everything we've ever detected with our telescopes, makes up less than 5% of the entire universe? So, what's the other 95%? Well, a huge chunk of that, about 27%, is one of the biggest mysteries in science. Dark matter. It's invisible, it's everywhere, and it's basically the secret puppet master controlling the cosmos. So, how did we even figure out something we can't see exists? It all started back in the 1930s with an astronomer named Fritz Zwicky. He was studying the Coma cluster, a massive group of galaxies. And he noticed something really weird. The galaxies on the outer edges were moving way too fast. Based on the amount of visible matter, the stars and gas he could see there, just wasn't enough gravity to hold them in place. They should have just flown off into deep space. It was like watching a merry-go-round spin so fast, the horses should be flying off. But they aren't. Zwicky proposed there must be some extra, invisible mass, providing the gravitational glue to hold the cluster together. He called this missing stuff dunkle Materie, which is German for dark matter. At the time, most people kind of shrugged it off. It was a radical idea, and the data wasn't perfect. But then, in the 1970s, another astronomer, Vera Rubin, came along. She was studying individual spiral galaxies, just like our own Milky Way. She was measuring how fast the stars orbit the center of their galaxy. Now, you'd expect stars farther out to move slower, right? Just like how Pluto moves way slower than Mercury in our solar system because the sun's gravity is weaker out there. But that's not what she found. Instead, the stars on the very edge of the galaxies were moving just as fast as the stars closer to the center. This discovery, called the galaxy rotation problem, was a huge shock. The only way to explain it was if the galaxy was surrounded by a massive, invisible halo of, you guessed it, dirt. Mata. Vera Rubin's meticulous work provided undeniable evidence that this stuff was real. Think of it like this. Imagine a spinning disk with weights glued onto it. The weights you can see are the stars and gas. But if the disk is spinning much faster than it should without flying apart, you know there must be hidden, invisible weights holding everything together. That's dark matter. It doesn't shine, it doesn't reflect light, it doesn't interact with light at all. It's completely transparent. It just sits there with its immense gravity bossing everything else around. So, we have all this evidence pointing to dark matter. But what is it? That's the billion-dollar question. Scientists are pretty sure it's not just regular matter that's dark. Like old stars or black holes. We've done the math, and there just aren't enough of those things to account for the missing mass. This means dark matter must be made of something entirely new. Some kind of particle that isn't part of our standard model of particle physics. It's something exotic and completely outside our everyday experience. The leading candidates for what dark matter could be are called WIMPs and Axions. Let's start with WIMPs. It stands for weakly interacting massive particles. The massive part means they have mass, which is why they have gravity. The weakly interacting part is key. It means they barely notice regular matter. A WIMP could fly right through you, right through the entire Earth, without hitting a single atom. This is why they're so hard to detect. They are the ultimate cosmic ghosts. To hunt for these elusive WIMPs, scientists have built some of the most sensitive detectors ever created. They're usually deep underground in old mines or tunnels. Why underground? To shield them from all the other cosmic particles that are constantly bombarding the Earth's surface. These detectors are essentially big tanks filled with a super pure liquid, like xenon or argon, cooled to incredibly low temperatures. The idea is that very rarely, a WIMP will fly through the detector and just happen to bump into the nucleus of one of the atoms in the liquid. This tiny collision would create a faint flash of light or a tiny bit of heat that the hypersensitive sensors can pick up. It's like trying to hear a single pin drop in the middle of a rock concert. So far, we've had some tantalizing hints, but no definitive gotcha moment. The hunt continues. Then there's the other main candidate. Axions compared to WIMPs. Axions are incredibly lightweight, maybe a trillionth of the mass of an electron. They are super tiny. They were originally proposed to solve a completely different problem in particle physics. But it turns out, They have all the right properties to be dark matter. They don't interact with light, and they don't interact much with regular matter either. One experiment searching for Axions is basically a giant, powerful magnet. The theory is that if an axion passes through this strong magnetic field, it could, on a very rare occasion, transform into a tiny flash of light, a photon that we can detect. Again, it's an incredibly difficult experiment, but the potential payoff is huge, discovering the identity of 27% of the universe. So we have these two main suspects, WIMPs and Axions. But the truth is, we just don't know. Dark matter could be something else entirely. Something even weirder that we haven't even thought of yet. Maybe our understanding of gravity is wrong. Some theories, like modified Newtonian dynamics or MONT, suggest that we don't need dark matter at all. Instead, maybe gravity just behaves differently on very large, galactic scales than it does here in our solar system. However, these theories have their own problems, and WIMPs explain all the observations, as well as the dark matter model does, especially when we look at the cosmic microwave background, the leftover glow from the Big Bang. The map of this ancient light shows tiny temperature fluctuations that were the seeds for all the structures we see today, like galaxies and galaxy clusters. Our simulations show that, without the extra gravitational pull of dark matter in the early universe, regular matter wouldn't have clumped together fast enough to form the galaxies we see. It would have just stayed as a thin, evenly spread out soup. Dark matter acted as the invisible scaffolding. It clumped together first, creating deep gravity wells, and then regular matter was pulled into these wells, eventually igniting into stars and forming galaxies. So, without dark matter, there would be no Milky Way, no sun, and no us. We literally owe our existence to this mysterious, invisible stuff. This is what makes the search for dark matter so exciting. It's not just about finding a new particle. It's about understanding the very foundation of our universe. It is about completing the cosmic inventory and figuring out the rules that govern reality on its grandest scale. Every time we build a new telescope or a new detector, we get a little closer to peeling back the veil. The discovery of dark matter, when it finally happens, will be one of the most profound moments in the history of science. Right up there with discovering the Earth goes around the sun or the discovery of DNA. It will fundamentally change our place in the cosmos. So the next time you look up at the stars, remember that the beautiful lights you see are just the tip of the cosmic iceberg. The real action, terrestrial mass, the real force shaping the universe, is hiding in the dark, waiting to be discovered. The universe is far stranger and more mysterious than we can possibly imagine. And that's what makes being a part of this journey so incredibly thrilling. Thanks for joining me on this cosmic mystery tour. If you enjoyed this and want to learn more about the incredible secrets of our universe, make sure to hit that subscribe button and ring the bell so you don't miss our next adventure. Let me know in the comments what you think dark matter could be. I'd love to hear your theories. Until next time, stay curious.